And this is our group, and we're looking to hire postdocs, so if you know about people who are interested in this type of topic, please send them to you. Okay, so let's start with a brief introduction. Let's take a single molecule in a cavity and assume that the cavity has such a single molecule strong light matter coupling such that you form hybrid states, the lower polariton and the upper polariton. Okay? This has been realized in various groups in the world, including the Baumberg group in Cambridge, Haran group in Weizmann, Pelton in Maryland, Baltimore, and I think and there are a bunch of other groups that are also trying to do something like this. Okay, and the key idea here is to use nanoplasmonic confinement of mode volumes of cavities to enhance light matter interaction. However, most of the experiments that are happening in this field, including the ones that Jun Kono discussed yesterday, are happening in a regime where it's about collective strong light matter coupling rather than single molecule light matter coupling, where now you put many molecules per mode volume, and now you don't have a nanocavity but rather a microcavity, and under those circumstances, even though the Rabi splitting increases dramatically compared to what a single molecule inside of these cavities would give you, namely by square root of n, you get all these subradiant states or dark modes that remain part of the same original molecular energy that you started with. Okay? Now, what is n? N is 10 to the 6 to 10 to the 10 molecules per mode volume of these microcavities, roughly. Okay? These are experiments from my colleague Wei Xiong in UC San Diego, where he puts microfluidic solutions of tungsten hexacarbonyl, and then he sees these splittings of energies due to the molecular vibrations of tungsten hexacarbonyl. The CO stretch couples to the 1983 weight number IR cavity mode, and then you see this very nice splitting. But bear in mind that you have a lot of dark states here, but you don't see them in linear transmission. But you will see them for chemistry and for nonlinear optics. And this is what you can do with electronic transitions of molecules. You get orders of magnitude larger Rabi splittings because the dipole moments are much larger for electronic transitions. Okay, so now I'm going to tell you about what we call the large N problem. The large N problem is the situation where you need to ask yourself whether a single cavity mode can really modify the chemistry of a huge number of molecules in the collective strong coupling regime. So then, most of us were grad students at some point, so we are used to asking the question, is there a free lunch? And just like the one we just had a few months ago. Okay, and if you were cynical about this, you would say, well, the light matter coupling per molecule, if you calculate it, is negligible, right? It's about like less than 1 micro eV here, nothing comparable to any vibrational or electronic energy scale of the molecule. So you would say maybe there is nothing in this problem, and although you see these beautiful polaritons, it's just an optical effect.
Sorry, how do you calculate that?
I mean, you can, for example, use COMSOL, you can estimate a mode volume, and then you take the transition dipole moment of the molecule, and then you couple.
So it depends on the volume?
Sure. Okay. But I'm just talking about in the microcavities.
Microcavities.
Sorry, per microcavity, you get like 1 micro eV. Okay? But then, more carefully, what the real statement is the following, is if you allow for thermal equilibration to occur, most likely you won't get anything because there are only 2 polariton modes and then, a lot of dark modes, right? 10 to the 6 to 10 to the 10 dark modes. So this is what we call the large N problem. And so what we're going to do instead is we're going to try to pump the system or induce some non-equilibrium initial condition.
The question you asked about this 1 micro eV.
Yeah.
Any energy in the cavity you divide by 10 to the 6 to 10 to the 10, you get a micro eV, right? Don't you?
Well, you divide over 1 over square root of n. Because, yeah, so the Rabi splitting, you divide it over that, then you get 1 micro eV. Okay. So then, what we're going to do instead is that we're going to focus on non-equilibrium effects, and I believe that has been a trending topic in this conference. And this is not something that only we have been saying, but other groups Joseph Botny, Gabe Nixon, Frank Wu have been saying similar things. Okay, so now I'm going to show you some experimental evidence that sometimes the cavity doesn't do anything, like for example in this case, where you put these molecules that have very interesting organic photophysics, you couple the electronic transition to a cavity, the photoluminescence kinetics looks inside and outside of the cavity exactly the same. Okay, so the cavity might as well just be a decoration, the polarities are just a decoration in that case. However, there are other strange situations, like for example, this experiment by my colleague Yuen, where he couples two different molecular species inside of a cavity that normally don't talk to each other, but via the cavity, now there is energy transfer between a set of molecules to the other set of molecules. Now, and then there is this experiment by my colleague Julia Callow in Northwestern, where she puts these molecular switches inside of an optical cavity, she pumps the system, and then she recognizes that the kinetics of isomerization inside of the cavity is faster than outside of the cavity. Okay, so sometimes the cavity doesn't do anything interesting, doesn't do anything remarkable, but sometimes it does. So then I would like to have an agnostic viewpoint on these, and then just build a tool to explain when would I expect something non-trivial, and when would I expect something completely mundane. Okay, so for that I need this tool. This is what I'm going to discuss. I'm going to first recognize that the molecular polarity problem can be thought of as a quantum impurity model. And then I'm going to show you a very neat method that we have developed recently to account for these complicated systems. Then I will discuss how we can get topologically non-trivial phases with using this type of ideas. And then I will finally conclude with the discussion of some experiments that resembles a lot to what we have been hearing about from Daniele Fausti and from Jerome Fai's talks, and, but I will leave it at the end. Okay. So a year ago, there was a student that came to my group from ETH, and then he wanted to do a master's thesis. So I asked him, why don't you run quantum dynamics on 1, 2, 3, 4 molecules inside of a cavity, and then look at trends, and maybe you can extrapolate about what happens in some thermodynamic limit and whatnot. And he got some nice plots, and but we still found the insights not very interesting, and we still found the interpretation rather difficult. And then what happened was that this very brilliant grad student, Juan Perez Sanchez, recognized that what I had asked Federico to do was something rather silly, because why do you compute the dynamics of n identical molecules if they are all exactly the same? So what you can do is exploit permutational symmetries. Okay, so this is a summary of what ended up being the method. So we call it collective dynamics using truncated equations called E, and it's not cute because Juan thinks he hates everything that is cute, but we still think it's cute. So the main idea is following, is that it's wrong to think about 1, 2, 3, 4 molecules. These molecules undergo all sorts of complicated dynamics, photochemistry, vibrational dynamics, electronic dynamics, and whatnot. The correct way to do this is to think about infinity and go backwards with corrections of 1 over n squared, so on and so forth. The result of this is actually really intuitive and very nice, which says that if you are interested in the thermodynamic limit of n goes to infinity, you only need to account for an effective molecule, one effective molecule in a cavity, and the key word here is effective, it's not the real molecule. And then if you want corrections of 1 over n, you need 2 effective molecules, and so on and so forth. Okay. So there is this method has a lot of resemblance to other methods that have been very successful in different fields of physics, like the 1 over n expansions. For example, there is this very neat tutorial article in Physics Today by Ed Witten that discusses how there are some problems in quantum chromodynamics that are very challenging when the number of colors is large and is some sort of dimension. But then when you take n to infinity and then you do expansions of 1 over n, you get the right answer seamlessly. Now, here at Harvard, Dudley Hirschbach, who got the Nobel Prize for Chemistry, he recognized that one could use these ideas for the molecular structure, electronic structure problem. And in particular, he noticed that electronic structure for molecules and for atoms becomes trivial in the d going to infinity limit, when the number of dimensions goes to infinity, because it becomes a classical electrostatic problem. And then if you do interpolations of 1 over d and so on, you get pretty accurate answers for d equals 3. Okay, so in the similar spirit, then we argue that when the number of molecules is gigantic, you know, even though you are faced with this seemingly scary problem, actually it becomes somewhat of a trivial problem, as I will discuss. Okay, so I want to think about this setup as a quantum impurity model where A is the photon and is coupled to all sorts of anharmonic, complicated, you know, electronic and nuclear degrees of freedom. And so I'm just going to show you 2 slides that show the derivation of cupping. Okay, so let's take the molecules. So each of the molecules is composed of a ground and excited potential energy surface. And these QIs can be a multidimensional vector of all sorts of nuclear coordinates. These can be very polyatomic molecules. And there can be much more complicated terms, but for illustration and for concreteness, I just stick to 2 surfaces. This is the kinetic energy of the nuclei, and this doesn't need to be harmonic. And then I have the photon, and then I have a light-matter coupling of the electronic transition of each of the molecules to the cavity photon. Okay, so G is a single molecule light-matter coupling, which is this micro-eV quantity that is negligible per molecule, but collectively they do much better. Okay, now, next what I'm going to do is I'm going to write formally the many-body wave function of the entire cavity, right? So I'm going to say, well, what is the wave function of the cavity in the first excitation manifold is going to be a superposition of a photon state or you know, an excitation in each of the molecules. And each of these coefficients is a multi-dimensional vibrational wave packet, right? Composed of all the nuclear degrees of freedom of all the molecules in the cavity. So that sounds daunting, but we can still formally write a multi-configurational expansion for these wave functions. And here is the first important step. The important step is to recognize that because all the molecules are identical, and we will leave the restriction in a moment of this identicality, if they are all identical, then there are a lot of symmetries of the different coefficients of the many-body wave function, right? If you swap 2 different vibrations or 2 different excitons, you will get the same coefficient. So the insight number 1 is that permutational symmetries imply that many coefficients are redundant in this problem. So knowing what a few molecules are doing is enough. And as far as I know, no one has really applied these tricks in the past to solve this problem. So we were very surprised about that. Now, the second insight I think is much more remarkable, and I believe is very elegant, which is the following. Is when you package all the information that is non-redundant of these coefficients, then you end up with coefficients that couple to each other by collective coupling, square root of n times g, followed by single molecule couplings, collective ones, single molecule, collective one, single molecule. So you end up, instead of having this very complicated quantum impurity model, you end up with some sort of a chain. And this chain has a very natural separation of timescales, which is of the collective and the single molecule, the collective and the single molecule couplings, and so on and so forth. So now suppose each of these coefficients are of the photon, matter, photon, matter, photon, matter. Suppose you start with the photon with all the molecules in the ground state. If you're doing an ultra-fast spectroscopy experiment, then 1 over g is going to be a very long time, so then you just stop here, right? So then what that means is that something extremely complicated, you reduce it to a very, very small Hilbert space. So the insight number 2 is that, okay, so this is just like what many people in this community already know. If you know how to package your information smartly, a lot of quantum dynamics problems become rather trivial. And in particular, that's what happened in this problem, right? The quantum dynamics of this system explores a very small corner of the Hilbert space for short enough times. Now, what I also want to emphasize is that there's a very interesting structure here of, if you think about this as a big matrix, so these are blocks, and they are, if G were 0, then this would be a block diagonal Hamiltonian, so there would be conserved quantities. But then G is not 0, so then these are quasi-conserved quantities. And the quasi-conserved quantities are very strange. They are the number of molecules that have phonons in the ground state. And I can explain this a little bit better in a moment. Okay, so where does this
these ideas have been showing up in different ways in the literature earlier, right? But then not systematically in this way. But an intuition that you can get that can convince you that this makes some sense is the following. There are these very interesting results, for example, for the spectroscopy of molecular aggregates. Molecular aggregates are these chains of molecules that are coupled by nearest neighbor dipole interactions. So in this very nice paper of Frank Spano, what he explains is that if you look at the photoluminescence of these molecules, of these aggregates, if they are delocalized across n molecules, the zero phonon line, the 0 to 0 transition, is n times larger than the 0 to 1 line. So in other words, going back to the ground state with no phonons is faster than going back to the ground state with one phonon, or with more. Okay? So this is also closely related to the fact that if you have a cluster of, say, molecules, and then you shine light and you ask for the Rayleigh scattering versus the Raman scattering, the Rayleigh scattering is always n times larger than the respective Raman scattering, right? So these are all related physics. Okay, so here's the main idea, right? So you don't think about 1, 2, 3, you go to infinity instead, and then you go back with corrections of 1 over n and 1 over n squared and so on. Okay, this is the calculation that you would do if you had a molecule inside of a nanocavity. This is the Schrödinger equation that you would evolve. Instead, what we want to argue is that this is the effective wave function that you would evolve if you have, say, 1,000,000 molecules coupled to a cavity. Notice they have a very striking resemblance, but there is this pesky projector here that makes all the difference. And I'm going to tell you physically what this means. If you have a single molecule in a nanocavity and you photoexcite the molecule, it could exchange energy with the cavity at all nuclear configurations. However, and this is very interesting because you can change dynamics away from the Frank-Condon region. However, inside of a cavity with like 1,000,000 molecules or so, if you photoexcite only, say, 1 of 1,000,000, like you stay in the first excitation manifold, what that means is that you excite a molecule, it can exchange energy with the photon as long as it's in the Frank-Condon region, but when it goes away from the Frank-Condon region, it just behaves like a boring old, a plain, boring, excited state of a molecule outside of the cavity. And this is a very important conclusion, right?
What about, let's say, other finite momentum cavity modes that would be able to decay that?
That's a very good point, but then I'm talking about when n goes to infinity. Okay, so first I'm going to try to understand n goes to infinity. What you are talking about are situations when you have finite size effects. But this is very reminiscent to what I have been seeing today, for example, in the talk of your own 5, where everything's about edges and very small corrections that are not thermodynamic, right? So when you have 1 over n effects, then all these things that you're talking about are important. Okay. Now, so physically, when I explain this to my experimentalist colleagues, they understand it faster than my theory colleagues. What they think about is the following. So you photoexcite a molecule, all the molecules that are responsible for the strong coupling are in the ground state. Pretty much 99.999% of them are in the ground state. And the very small fraction that you have excited moves away from the Frank-Condon region. It cannot benefit from its remaining counterparts that are in the equilibrium geometry of the ground state. Okay. So now we get a lot of criticism saying, well, molecules are not really identical to each other in solution, so there is always disorder. Okay. So it turns out that with disorder, this method still works very well. The way it works is the following. So suppose, for concreteness, let me consider this situation of a photoneous electron transfer model where I photoexcite the molecule. This is a donor state, and it transfers its population to an acceptor state, and you call this the probe. Okay? So now, let's consider that this excitation energy has a distribution of frequencies. And, if I were to do this brute force, I would say, well, there are like 10 to the 6 different excitation energies, so I cannot use permutational symmetries. But quantum dynamics, and especially spectroscopy, is rather, gentle and nice to us. And what it does, it gives you very small projections that, it gives you like spectra that have very limited amount of information. And especially if you're interested in short times, you you look at what the uncertainty principle tells you, and you say, well, if I'm interested on a signal up to a time big T, then all I need to care about is resolution in frequency of 1 over that big T. And if you do that, then you notice that instead of simulating 10 to the 6 molecules, you only need to simulate, 10 different molecules. And what we found is that you don't even need to simulate 10 molecules. You can take a single effective molecule and put 10 different electronic states there. And that actually scales way better than if you take 10 molecules, because if you have 10 molecules, you need to multiply the Hilbert space of the vibrations of each of the molecules. Okay? So if you bin this and then you discretize, then if you are interested again in short times, then you can repeat the same ideas of topic. Okay, so let me tell you a few interesting conclusions of these calculations. The first one is that it turns out that Rabi splitting increases with moderate amounts of disorder, and as everyone knows, when the disorder becomes very large, then the Rabi splitting becomes negligible again. This strange effect of moderate amounts of disorder increasing the Rabi splitting can be easily understood through a perturbative picture, but I can explain it if there are questions about this. But here's the important lesson that needs to be conveyed to the community. If you get, like, say, a Rabi splitting that is 10% of the optical gap, that doesn't mean that you're in ultra-strong coupling, right? So the Rabi splitting is a false indicator of ultra-strong coupling because disorder exacerbates the Rabi splitting, and maybe your collective light matter coupling was, say, 0.07 of the optical gap, but then the disorder augmented it. Number two is reactions can be suppressed when you couple to the cavity, and this was very well conveyed by Felipe Herrera and Frank Spano, and also by Johannes Feist a while ago, and they call this polar decoupling. And the way they explain it is that the energy exchange with the cavity is so fast that it doesn't allow for the nuclear dynamics to ensue, and because the reaction involves nuclear dynamics, then you quench the reactivity, but when you increase the disorder, you recover the reactivity exactly as outside of the cavity. So nothing interesting when you have a lot of disorder. But you could also enhance the reactivity. For example, if you have a donor state that is lower in energy than the acceptor state, you can make the donor state become closer in resonance to the acceptor state, and you can enhance the reaction compared to outside of the cavity. But then when you add disorder, then you asymptotically recover what you get outside of the cavity. Now, here is a very illustrative example, in my opinion, that shows that, for example, say two spectra, one outside of the cavity, which shows a very broad Gaussian of the molecular line shape, and then inside of the cavity, the same ensemble, but inside of the cavity. Notice that the dashed black and the solid black, they give pretty much the same yield of the product. And many people think, oh, I form polaritons, I see this beautiful splitting, then I must have changed the chemical dynamics of the system. This is highly misleading, and the resolution to this discrepancy is very easy. Linear absorption is a consequence of short-time dynamics. Because the reaction happens at longer times, then even though you see a beautiful splitting here, it doesn't mean that the reaction has been changed at all. Okay. So here's the summary number one. There are many interesting optical experiments that have been shown demonstrating changes in chemical dynamics upon polariton formation. And we believe that this COT-E gives you a very intuitive, very simple way of understanding what are the physical ingredients that you need to control reactivity. And it's also very numerically efficient, and is connected to all these quantum impurity models. And the cavity can indeed change reactivity, photochemistry, and a possible control strategy is to align, energy levels that were misaligned outside of the cavity. Okay, so what do you do with this? So,
Joe,
yes.
Is your thing out of battery?
I don't know. Hello. Maybe it is.
Yeah, it's
Because it's on.
Does it show that it has
On.
battery bars?
I don't know. But I think I speak loud enough, so it's fine, no?
Yeah, but
Okay, let me continue and then.
for the recording.
Okay.
Let's switch it on.
Hello. Okay. So now, let's consider, okay, so let's think about molecular polaritons as quantum impurity models. 2 years ago, I had this very illuminating discussion with Professor Nancy Macri from University of Urbana-Champaign, where she explained to me that if I have an impurity coupled to a very anharmonic path, in the thermodynamic limit, I can always assume that the path is harmonic. So this is basically what people were talking about yesterday, the Holstein-Primakov transformation, but it's a little bit, it's more general, right? Like it's not just for spins, but it's for also multi-level systems. Now, the historical origin of why Nancy was interested in this type of problems is actually quite interesting, and maybe you guys will appreciate it. So, so back in the days, Rudy Marcus, who won the Nobel Prize for Chemistry, he was interested in modeling electron transfer reactions. And at some point, he came up with this very simple model of two parabolic potential energy surfaces that couple to each other. And surprisingly, that rate theory gave extremely accurate results, but no one believed why such a complicated condensed phase system would end up giving parabolic potential energy surfaces. And the resolution is that, in condensed phases, because you have many anharmonic degrees of freedom, then at the end you can bosonize the system in some way, and you get these parabolic potentials. And this is a very nice paper that explains why you do that. Okay. Now, if I think about the photon as the impurity and the molecules as the path, and I do this linear response limit, then, not surprisingly, I just recall very classical optics, right? So, okay, so now the molecular polariton problem becomes harmonic in the thermodynamic limit. This is not surprising. And all you need, because you have just a harmonic oscillator coupled to other harmonic oscillators, all you need is the linear susceptibility of the ensemble. What I think was a little bit surprising to me was that it doesn't matter if the molecular system is in the ground state or is in a thermal ensemble or is even in a non-equilibrium, is in some excited distribution, as long as the initial density matrix is stationary and factorizable, you can do this. Okay, so we wrote this recently with Argadit Conner, and this is not super new, but I feel like a lot of people in the community don't know this because for example, people run simulations with many molecules and they make conclusions that what this is saying is that you don't even need to do those simulations. You just do the simulation of the molecule outside of the cavity and then you plug it into the transfer matrix formula. Now, so all of this was said in some way or another by Jonathan Killing, but Jonathan is very smart and I don't understand his papers, so so we wrote our way, our for dummies way to understand all of this. Okay. Now, so what do you do with this? Well, for illustration, let me consider ensembles of two-level systems. So for example, if all of them are in the ground state, you get a very large Rabi splitting in transmission, absorption, and reflection. If you photoexcite 25% of the molecules, then the Rabi splitting contracts by 1/√2 because the Rabi splitting is proportional to the square root of the polarization. So you need to, if you have 3 minus 2, you have 2 compared to 4, so you have 1/√2 smaller Rabi splitting. And if you saturate the ensemble or you have infinite temperature, then your system just sees a transparent medium and it doesn't create polaritons. And I saw a poster yesterday by the June Konos group that shows exactly this case, right? So what do you do with this? So importantly, you can create these situations with optical pumping, and as long as the matter and the cavity decouple, then you can use the effective permittivities due to these states. Okay, so what do you do with finite n? If you have a finite number of molecules, it turns out that even the linear response of the cavity tells you about the nonlinear response of the molecules. Why is that? If you shine light through the cavity, then the molecule can bounce its energy back to the cavity, and this light can re-excite the molecule and so on and so forth. So you might think that a linear response of a cavity involves all sorts of nonlinearities of the molecule. And this is true for small n, right? So there's a very nice expansion of 1/n, 1/n squared, and so on, that tells you what are the finite size effects. So in principle, if you have a linear spectrum of these systems, you can also extract the nonlinear response of the molecules if you have a small number of molecules. Now, So what do we do with this? So a few years ago, we were interested in creating topologically non-trivial states of molecular aggregates or systems associated to molecular aggregates. The problem that we had, that we kept facing, was that the magnetic fields that we needed to deploy were pretty large, like 20 Tesla or so. So, you know, we talked to experimentalists, and they always told us, oh, this is a very difficult experiment. So, so instead, what we thought, maybe we can use optical saturation, like you pump the systems, they decohere, and then, for example, if you take this porphyrin, which you can think about this as a three-level system with a ground state and a plus state and a minus state, if you pump circularly polarized light and you saturate, say, the plus transition a little bit, then you will have effectively broken time reversal symmetry in this effective Hamiltonian. And if you calculate the Berry curvature and integrate, then if you create a population imbalance between the plus and the minus states, you will, not surprisingly, get non-trivial, you know, topological polaritons. But if you saturate the transitions equally, or you don't saturate, then you don't get topologically non-trivial bands. Okay, you can also do this with lanthanide impurities or with 2D materials. And okay, so there was a really weird thing that we faced when we were doing this analysis. Maybe since you guys are experts on this, so maybe I just open the floor for discussion on this. So we didn't see any bulk boundary correspondence in these problems. And the reason is because if we don't pattern the sample, right, so if you just put the slab here inside of the cavity, then at the level of the Hamiltonian, there is no spatial information because the molecules only know about the spatial information through the light field. And the light field couples to the molecules through a phase, and the phase, you know, is the same mod 2 pi, so then you never see this spatial information. So the question I want to raise is, what is the analogous phenomenon to bulk boundary in this type of polaritons? And I would like to know, maybe there are people here who know this better than me. Okay, so when n goes to infinity, so we trivially recover classical optics, and this is true also for a lot of nonlinear optical experiments, nonlinear spectroscopy, pump probe, photon echo, 2D spectroscopy, all sorts of things, because these polaritons decohere so quickly that that the light and matter degrees of freedom decouple, and then you can just go back to, you know, classical optics. And this is true when you are in the thermodynamic limit, but then in many of these experiments at short times, this is what's happening. And then you can exploit these optical saturation effects to give rise to topological polaritons, but there is this lacking bulk boundary correspondence that I don't know where it's hiding. Okay, so this is work done by Sinana Panir-Sivajyoti, and this is in Photomech now. Okay, so I thought that because this is a topological whatever conference, I think people are going to care about this one. So I was very sad that Gil Rafael didn't show up yesterday, but a few years ago, Angel Rubio organized a conference in the Flatiron Institute, where Gil explained that you can have zero-dimensional versions of the quantum Hall effect as long as you have two incommensurate frequencies driving a speed. Okay, so that's roughly, so you know, omega 1t and omega 2t serve as kx and ky. And then you have pumping of energy, nonlinear energy conversion from omega 2 to omega 1, and it's quantized. Now, I went back to San Diego and I showed this paper to my student Kai Schwedicke, and also this very nice paper by Moshe Shapiro, which I think has very close connections to ITAMP, and I think he even has papers with Jose. And Moshe recognized that if you have molecular enantiomers, namely molecules that cannot superimpose onto their mirror images, if you multiply 3 of their dipoles, then you pick up a very phase of -1 compared to the other enantiomer. Okay, so Kai, in a very nice work, he generalized this idea and then shows that the topological frequency conversion is quantized in a Chern number, and the Chern number turns out to be miraculously this product of dipoles that Kral and Shapiro have thought about, right? So then if it's, say, one enantiomer is +1, if it's the other enantiomer is -1. So I just want to highlight that even in zero-dimensional systems, you can get all sorts of interesting topological effects. Okay, so in the remaining part of maybe 2 minutes or so, I'm just going to briefly tell you about a subject that we still don't fully understand. So a few years ago, Thomas Edison coined this term called micropolaritonic chemistry, where he just puts molecules in a cavity and he doesn't pump the system. So this is key. He doesn't pump the system. He shows strong coupling of, say, the reactant vibrational modes to the cavity, and then he sees suppression of a reaction as per notice from this Arrhenius plot, where the activation energy is presumably decreasing compared to outside of the cavity. Okay. There are all sorts of repetitions of this experiment that have been reproduced. Some of them have not been reproduced. So this is kind of like a confusing subject. So we wrote a review where we say that none of the theories that have been proposed so far can explain all the different observations in the experiments, not even my theory, Hans' theory, Angel's theory, no one's theory can explain what's happening right now. So then, and the real problem is the large N problem, right? Reactions are local, polaritons are delocalized. Why on earth would the reaction care about this delocalized object? You know, like there are these entropic penalties of the reactions if they pass through polaritons. Okay. So, okay, I'm not going to talk about polariton condensation because I don't have time, but you can in principle use polariton condensates to exacerbate the rates of polaritons. But a few years ago, I met Matt Sheldon, and Matt Sheldon showed me this very strange experiment where he has copper sulfate pentahydrate, and then it normally dehydrates to its trihydrate form at 47 Celsius, nominally 47 Celsius. Okay? And then apparently under strong coupling of the OH stretches of the water, then the transition temperature changes to 39.5. So we spent, you know, so many months thinking about what could be going on because this only happens at resonance. And we couldn't come up with anything because we had tried so many things in the last 5 years. So the only possibility we came up with was a heat transfer model that I think is very reminiscent to what Daniele Fausti showed, where we are arguing that maybe these systems have very poor heat conductivity, and the vibrational strong coupling is creating additional channels of heat transfer, namely radiative heat transfer, that allow you to homogenize the temperature across the sample. So in principle, you know, the real transition temperature is not changing, right? Like it's close to 39.5 always, but then from the heating stage, it looks like it's 47 when you don't have vibrational strong coupling. Okay, so I know it sounds crazy, and I believe it's a bit crazy, but I don't know what else I can come up with. The real elephant in the room is why is radiative heat transfer bypassing conductive heat transfer? And I can be honest with you, I'm very skeptical about this, but maybe there are situations that are surprising, and maybe this is one of them. Okay, so with that, I tell you, when you pump the system, we can calculate the dynamics, we can understand a lot of things, you have a lot of opportunities in this field. When you don't pump the system, it seems that there are also opportunities, but I don't understand what's going on. I believe that all of these are mesoscopic effects of non-equilibrium, but I am open to other possibilities. Okay, so with that, thank you for your attention.
Thank you. We have time for one or two. In this chemistry, what strikes me always is on one side the large N problem, but the other aspect is the large T problem. Meaning, usually, let's say the reaction rate per molecule and per unit of time of motion is extreme.
It's a rare event, yes.
So, in a sense, can't you sort of get a significant difference by looking at fluctuations?
So we were already there, and actually Johannes also tried that, I tried that. So we came up with a model that is a little bit esoteric, where if you have very strange geometries of the molecule, because of these rare events, you can have, even though if a reaction is very slow, even if these channels are entropically penalized, they could still matter. But if you run computational chemistry, you can never find situations like that. So it sounds plausible, but I haven't been able to find those real examples. Yeah.
While our next speaker is getting up, is there any other question? Please.
Just Yuen, one question about topology. You were talking about the topology in the case of driven molecules. How do you define it?
So
Because
in our case,
I know
we're
that
just looking
bishop
at.
in an elephant is not possible to define. Then I
Say
say
again?
that up front, the topology is only possible in the adiabatic ground state. In a pumping system, you cannot define a topological state.
Yes. So
Then how do you define it?
okay. So if you believe in the effective Hamiltonian that you create when you have these effective permittivities, which I believe that okay within the time scale, if you believe this is topological, then what I'm saying is true. But of course, it's going to be non-robust because it's going to decay, and it's going to this topological protection that is promised is not going to be there. Yeah, I agree.
You see it, no?
Yeah, it's because of their instability. Yeah.
With that, let's thank our speaker one more time.